Alright, let me remind you the basics about partial fractions. So, in the partial fractions lecture, we saw this main idea. We were going to break up a fraction with a complicated denominator into a bunch of simpler fractions with nicer denominators. And remember that the simple fractions are going to take different forms depending on the denominator that you started with. So we saw that there were 4 different cases that you can split into. The first is if you have distinct linear factors in the denominator. So the only thing that we really have to worry about in the numerator is that, remember, we want the degree in the numerator to be smaller than the degree in the denominator. In this case, the degree of the numerator is 2, the degree of the denominator is 3. So the denominator wins, and that's what we want. So we want that denominator to have a bigger power than there is in the numerator. And when that's the case, you can do this splitting. If there are distinct linear factors down here in the denominator, then each one of those is going to get their own fraction, and you just need to figure out the number that goes up top. So A, B, and C are going to be numbers. Your final answer is going to look like this, but you need to figure out what A, B, and C are. So you need to find the values of A, B, and C that solve this equation. And in order to do that, you are just going to multiply both sides by this denominator. So you sort of clear the denominators everywhere, and then you can plug in particular values, or you can match coefficients to find the values of A, B, and C. And we'll do an example of that at the end of this video. But you can also look back at all of the examples that we did together. If there are repeated linear factors, like this x cubed, then, so that's x is the linear factor here, but it's repeated 3 times. This is an x times x times x. So that linear factor appears more than once. When you have linear factors that are repeated, then for any linear factor that's repeated, you're going to have new fractions for every power counting up to the top power that you need here. So you would have a power of x, a power of x squared, and then a power of x cubed. And so those 3 become your denominators here. Each one of them will get their own coefficient up top. So they'll have an A, B, and a C. And you need to find those values. For this x plus 2 factor, that's also going to get its own fraction. So the same rules apply for distinct linear factors, even if they appear alongside repeated linear factors. Okay, so if you just have a unique linear factor, it's still going to get its own fraction like this. And for this one, your answer would look something like this, but you would need to find A, B, C, and D. Something sort of similar happens when you talk about irreducible quadratic factors. We did one example of this together, but let's look at this example. So here, the degree in the numerator is 1, the degree in the denominator is 4. So that means that we can use partial fractions here, but you should try factoring the denominator if it's not already factored for you. So in the 2 examples that we've talked about already so far, the denominator has already been factored. Here the denominator is not fully factored because this is a difference of squares. So we could actually rewrite this fraction, as a 7x minus 5 over a x minus 2 times x plus 2 times x squared plus 4. And now these are distinct linear factors. This is an irreducible quadratic. So it's an x squared plus 4. The roots of this are purely imaginary, so they're plus or minus 2i. So that means that we're not going to be able to factor this using real numbers. And therefore, we're stuck with this unfactored form. This is an irreducible quadratic. When you have irreducible quadratics, they also get their own fractions. So we're going to get a fraction with an x minus 2, we're going to get a fraction with x plus 2, and we're going to get a fraction with the irreducible quadratic. But the thing that goes above an irreducible quadratic is not just a number like c. Unfortunately, it's a linear factor, so you would get a cx plus d. So above any irreducible quadratic, you're going to have 2 numbers here that you have to figure out. You'll have a c times an x plus a d, and you need to figure out all of these capital letters, a, b, c, and d. Okay, so your answer will look like that, but again, you have to figure out a, b, c, and d. And the procedure for figuring out a, b, c, and d is the same for all of these. You always just multiply both sides by this denominator that you started with. That will clear all of the fractions. And then at that stage, you're either matching coefficients or you're plugging in particular x values to try figuring out a, b, c, and d. Usually, it's a good idea to plug in any roots that you see. So positive 2 and negative 2 would be good things to plug in this problem. But we'll do a plug-in example in a second. And then lastly, there's one other thing that can show up, which is repeated irreducible quadratics. So in this example, the degree in the numerator is 2. The degree in the denominator is 5. So if that surprises you, maybe think about this for a second or pause the video. But this is a degree 1 thing times a degree 4 thing because you have a quadratic that's being squared. So if you were to multiply all of this out, which you can do if you want to, you would end up getting a degree 5 thing. So the degree in the denominator wins, so that means that I should be able to split up into these partial fractions. Now, we want to factor this if we can, so let's try factoring this. If I were to try factoring this, this is a monic quadratic, so that means that I could look for two numbers that multiply to give me the last number and that add up to the middle coefficient, but I can't think of any numbers that multiply to give me 2 and that add up to a positive 1. So that means that I'm stuck. I could factor this as x minus its first root times x minus its second root, if I can figure out what the roots of that quadratic are. In order to figure out the roots of that quadratic, I would need to use the quadratic formula. So I would have that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And in this case, that would be a negative 1 plus or minus the square root of 1 squared minus 4 times a is 1 and c is 2 all over 2 times a. And that would be negative 1 plus or minus the square root of, on the inside here, you would get a 1 minus 8, so that's a negative 7 on the inside. And notice that here you're taking the square root of a negative number. That means that these expressions, or these roots, are going to be complex. So that means that we won't actually be able to factor this using real numbers. So in this class, we just call this an irreducible. And when you have irreducibles like this, then what you do is you will still have a splitting. So we have one linear factor that's not repeated, so it's going to get its own fraction. And then we have an irreducible quadratic that's repeated twice. So the repeating mechanism is the same as it was up here. So here there was a triple repeat, and we got 3 separate fractions, one for each power, counting up to the top power. We're going to have the same thing here. So we're going to have one fraction that just has an x squared plus x plus 2, and then we're going to count up until we make it to the top power here. So we'll count up to squaring this irreducible quadratic. So it's the same idea that we had for repeated linear factors. You just count up the powers until you reach the power that you actually have in the denominator. And the same rules apply for the numerators here. So for each of these split fractions, you should have a number times x plus another number. So we would get a bx plus c and then a dx plus e. And in this problem, this would be your answer, except you have to first find a, b, c, d, and e. Okay, so that's the idea for the splitting. There's one other subtlety that I want to mention before we finish out this example, and that's that if the numerator's degree is bigger than or equal to the denominators, then you have to use long division first before you can actually split into these partial fractions. So for example here, the numerator's degree is 3, the denominator's degree is 2. So if I wanted to use partial fractions here, I unfortunately can't immediately split. What I have to do is maybe come over here and do some long division. So I'll write an x cubed plus a 2 on the inside. I'm dividing that by an x squared minus x. When you do long division, you take the first thing on the inside and divide by the highest order term on the outside. So that would be an x cubed divided by x squared, which is x. Once you find a new term in the quotient, you multiply by this outside stuff. So that would give you an x cubed minus an x squared. You take that product and you subtract it off. So this would be x cubed minus x cubed, that's 0. this would be a positive x squared because this minus sign applies to both of these terms in the product. So you would get a positive x squared as your remainder, and you can bring down the rest of these terms as your further remainder. So you would get an x squared plus 2 as your remainder. You're not quite done here because x squared is divisible by x squared still. So you have to keep going until the degree here is less than the degree out here. So you have an x squared plus 2 that we're trying to divide by an x squared minus x. You again just take the highest order term on the inside and divide by the highest order term on the outside. So that would give you x squared over x squared, which is 1. So 1 is going to be the next term in the quotient. And then you multiply that 1 times the stuff out here. So that would give you an x squared minus x. You subtract that off. When you do that, you'll get x squared minus x squared, which is 0. Negative negative x gives you a positive x, and you can bring down the 2 again. So x plus 2 is your current remainder. This will actually remain your remainder. So you would just get an x plus 2 as your remainder term. That's because x is not divisible by x squared. So because the degree of your remainder is now smaller than the degree of your divisor, you're done. So this is your quotient up top, and this is your remainder. Now remember that whenever you have a quotient and a remainder, that means that you can split this original expression into the quotient, which is x plus 1, plus the remainder, which is x plus 2, divided by the x squared minus x, because this remainder, x plus 2, hasn't yet been divided by the x squared minus x. So we can split like this, and now this is something that we can use partial fractions on. So for this x plus 2 over x squared minus x, now we can use partial fractions on that. To use the partial fractions technique on this, you would want to factor the denominator. So I would factor an x out from the denominator to get an x times x minus 1. Those are distinct linear factors, so that means that this should split as something over x plus something else over x minus 1. And we'll be done as soon as we find out what a and b are. So I'm just splitting this term into these two terms. So let's figure out what those are. We have that x plus 2 divided by x times x minus 1 is equal to a over x plus b over x minus 1. And we're trying to figure out what a and b are. In order to do that, we can multiply both sides by this denominator. So if we do that on the left side, we'll have x times x minus 1 times this fraction. And if we do that on the right side, we'll have an x times an x minus 1 times all of this stuff. Now on the left side, you can cancel these x's, and you can cancel these x minus 1s. So that means that on the left side, you should just get this this numerator. That's what you should always get. So the left side will just be the numerator because you multiplied both sides by its denominator. On this side, whenever you take this and distribute it, when you distribute to the a term, you'll be able to cancel the x's, but you won't be able to cancel the x minus 1. So you would get an a times an x minus 1 for that first term. And then similarly, whenever you distribute to the second term, you'll be able to cancel the x minus 1s, but you won't be able to cancel an x. So you would get a bx there. And now you want to plug in particular x values so that you can hopefully figure out the values of a and b. Here it's a good idea to maybe plug in the roots of each of these. The root for this first one is positive 1. The root for the second one is 0. So I would plug in x equals 1. If x equals 1, then the left side is 1 plus 2, and the right side is a times 1 minus 1 plus b times 1. That means that 3 is equal to 0 plus b, and therefore b is 3. So that's one of the things that we were looking for. We can also plug in the other root. So I would plug in x equals 0. That means that the left side is going to be 2, and the right side is going to be a times 0 minus 1 plus b times 0. And that right side simplifies to be negative a. So that means that 2 is equal to negative a, which means that if you multiply both sides by minus 1, negative 2 equals a. So we now know that a is negative 2 and b is 3, and then to finish you would just scroll back up and replace a with a negative 2. You can either put the negative 2 up here, or you could put the minus sign in front of the fraction, so you could write it like that. Okay, so that or that, either way is fine. And then b was 3. And now we've split that original expression into a few simpler pieces. Okay, so that's the partial fractions technique.